All right, great. I assume you're hearing me well. So thank you very much for the invitation, and my sincere apologies that I wasn't able to make it to in person, but I had some last minute passport problems. So I hope I'll be able to make it up today with a clear online presentation. So what I'll talk about today is a concept that we call phononic subsurfaces. And so what I'll show you towards the end of this talk is what I think is a quite an interesting phenomena, whereby we not only look at uh, scattering mechanisms of elastic waves in a solid, as we always like to, you know, examine when we're studying metamaterials and so on, and phononic crystals. But perhaps what is unique here is that we have an elastic solid, a phononic material, that is interfaced not just with a fluid, but with a flowing fluid. And the scattering mechanisms that I'll share with you today are synchronized, in fact, perfectly synchronized between the two media, between the elastic medium and the flowing fluid. We've been exploring this problem in the context of controlling fluid flow and achieving things as ambitious as delaying transition to turbulence, for example, and so on. So let me get started. So I'm going to take a step back, give a brief intro. I think we'll all remember from our textbook fluid mechanics this typical picture showing a flow over a surface and experiencing transition. So you've got the laminar portion, then the transition, and then the turbulence. And what is, for us as wave propagation people, I think what is really interesting is that the core principle that influences transition is in fact a wave phenomena. So these are instabilities in the flow. These are not acoustic waves. In fact, these are fluid waves. So these are components of the flow field, the UVW flow field, and they're essentially eigenmodes that emerge in a typical flow environment over a surface. And these modes can be actually characterized by solving the linearized form of the Navier-Stokes equation. So you get a frequency versus Reynolds number picture that tells you exactly in this map which modes are stable and which ones are not. So we can actually appreciate this by doing a full-fledged direct numerical simulation. This is from my late colleague Sadat Berenjen's group, showing essentially a breakdown of a flow transitioning to turbulence, and you can clearly see the elements of wave motion there. So you've got an instability that is growing unless you do something to it, and essentially that causes transition to turbulence. Now, this is really important because laminar flow is known to give us relatively low skin friction drag, whereas in a turbulent boundary layer, the skin friction drag is very high. So if you can delay the transition, then you significantly reduce the drag over the surface of an aircraft wing, for example. So that's our goal. We would like to intervene somehow into this instability so that we delay transition. The implications cannot be overstated. I mean, this is just a few examples I'm showing here. If you look at the global airline industry alone, $210 billion spent annually on fuel, and the percentage of air travel is continuously growing in sea, because this obviously applies to marine vehicles as well. If you look at that statistic here in terms of its environmental impact, and then other, a wide range of other applications, similar applications, whether land vehicles, wind turbines, long-range pipelines, and so on. All right, so now if we can intervene to stabilize an unstable wave to delay transition, well, in principle, we can do the opposite as well. We can intervene to destabilize that same wave. In other words, make it transition to turbulence or transition or grow quicker. And that has its own benefits as well. In aerodynamics, it would help with delaying separation. So that has its obvious benefits, reducing the possibility of stall, for example, or reducing form drag. And then it can also be used for enhancing mixing or combustion. All right, so now let me sort of take a minute and zoom into the flow field itself and what it constitutes. So essentially, we can think of a decomposition of the flow field. This is commonly done in fluids analysis, where we decompose the field into a mean component. So in the case of a channel flow, this is the familiar laminar profile. And then the instability will be superimposed on that mean component. So you get a total, you get a total component that's the sum of both. And the instability as it grows, as I was showing you in the previous cartoons, essentially what happens is that it grows and it starts influencing the profile itself. Now, this is an exaggerated view, but it just gives you a sense that you start getting momentum transfer distribution, and essentially that's how a profile starts transitioning and acquiring the characteristics of a turbulent profile rather than a laminar profile. So what is key, obviously, in this picture here is that energy is being transferred from the mean flow into the instability. So that's the growth mechanism. And what we would like to do is to intervene into that mechanism. So I'm gonna sort of take a couple of minutes of an aside, if you will, right now, and jump from fluid dynamics to structural vibrations, and I'll just review, extremely basic principles in vibrations, but I just want to review them to put things in context. So if we just have a structure, some general structure, and we're exciting it harmonically from the top, and suppose we're measuring by simulation or experiment the velocity at the top, at the point where we're exciting. So we will get a frequency response function that looks like that with its resonances and anti-resonances. If we look at a resonance, for example, at a frequency where we have resonance, and we plot the velocity, I'm going to call this the input velocity because it's at the input point compared to the input force, I'll see something like that. And you can zoom in just to see sort of like the harmonic signal. Now, on the other hand, in contrast, if we do exactly the same experiment and excite at an anti-resonance, we will see something like this at the bottom. And immediately you can see that the input velocity at an anti-resonance overall is less than the input velocity at the resonance, even though the forcing is the same. But that's the whole definition of resonance versus anti-resonance in a finite structure. And you can plot the energetics. So you can plot the input energy under the resonance conditions, and then you can plot the input energy under the anti-resonance. So the structure itself is accepting less energy. You need to do more work to put the same amount of energy under anti-resonance versus resonance. So this picture that is very familiar to us in structural dynamics, essentially what we'll do is we'll extend that picture so that it applies not only in a structure, but applies in a continuation between a structure and a flowing fluid with an instability. So the manipulation of resonances and anti-resonances will take place across both fields, the elastic material, the elastic structure, and the flowing field, the flowing fluid. So with that in mind, if I now go back and look at the same picture that I showed you before, essentially we now have conceptually, at least at this point, we have an opportunity to interfere into the resonance mechanisms, the resonance mechanism at the very fundamental level that underlies this energy exchange between the mean flow and the instability. And from a relative perspective, we can actually transfer it. Reverse it. So rather than energy continuously going from the mean portion to the instability, we'll reverse that trend. So the energy will be from a relative perspective, the energy will be going back to the mean flow. And if we can achieve this intervention, then essentially we achieved our goal. We're able to stabilize that instability. So that's the conceptual framework. If we now look at how we do this, we're going to start with a channel flow. That's the easiest, and we'll essentially look at a rather simplified model of a channel flow. So the top and bottom surfaces are rigid, and we will select a portion in the bottom surface and replace that rigid portion of the wall with a phononic crystal. So we all know in this audience what a phononic crystal is, and in this case, it's just a repetition of ABS plastic and aluminum. And we're going to introduce an instability. So this is the picture we have. So again, I have one more cartoon for you. So imagine that instability traveling, and it's essentially it's a wave. It's a harmonic wave, but in the flow field itself. And as it flows, it's constantly exciting the bottom wall. So if you're the wall, you're constantly feeling vibrations coming from the top and excitation. So obviously the rigid wall doesn't care, but the elastic medium will. So the elastic medium will admit a wave. So an elastic wave will be generated due to this excitation from the flow wave, and it'll travel through the phononic material. And then the underlying premise is that we'll be able to design, in principle we should be able to do so, design the phononic structure in a manner such that when that elastic wave reflects and transmits back into the flow, it gets manipulated. So it comes back essentially at a different phase in the manner that we desire. And if we can have it return at a negative phase, then it will destructively interfere with the original incoming wave, and then you get a stabilization. The amplitude of the flow wave will get subdued, and this is all happening passively and in the steady state. I mean, the cartoon implies a transient scenario, but this is all happening in the steady state. All right, so let us look now at how do we do this. So essentially, we need 4 plots. We like to call them the 4 key characterization plots. So we're not doing any simulations yet. So this is all offline. We're putting on our phononics hat. So we design the unit cell such that it exhibits a certain dispersion diagram as shown here. And then we're obviously turning that phononic material into a phononic structure, a finite structure. So it's not infinite anymore. That's obvious. So then we can obtain a frequency response function just like the one I showed you before. So this is exciting at the top and measuring at the top. And corresponding to that, there's a phase. And you can see the band gap there shown in gray. And then what we can do is we can multiply the amplitude by the phase and obtain what we call a performance metric. So this performance metric is shown at the bottom. And anywhere above the 0 line, the performance metric will be corresponding to in phase, and anywhere under it, it'll correspond to out of phase. And to the extent we have resonance or anti-resonance, the amplitude of that performance metric will be affected. So then the idea is that suppose we align this design with the specific frequency of the instability we're interested in controlling. So suppose, as one example, we have an instability in the flow that is lying at that specific green frequency, right? So if you look at the bottom, it hits the performance metric at a negative value. So that implies that should we apply that phononic structure to that system, that phononic structure will stabilize the flow. It'll give us destructive interferences into the flow field and reverse the energy trend. On the other hand, if that instability has a frequency that is red frequency, then that will intersect a positive value of the performance metric. So that will give us a destabilization. So we will get constructive interferences from the elastic field contiguously and extending into the flow field. So this is the idea, and essentially, we can look at this as a theory. We call it a theory of phononic subsurfaces, and it's a theory in the sense that it allows us to predict exactly what will happen to the instability field in the flow, and subsequently to very important events like transition and separation and so on, simply by analyzing the phononic structure offline. So we don't need to even run a simulation to see what will happen. We should, in principle, know a priori what will happen to the flow. And in fact, that really is it. I can stop there, but the rest of the talk will be simply to test this theory. So I'm gonna go over a series of simulations, fluid structure simulations, to show you how that works. So the way we'll do it is we'll essentially introduce a base field as an initial condition in a channel flow, and add to it artificially an instability. We will separately solve the Orr-Sommerfeld problem. So that's the linearized Navier-Stokes to get the instability modes, as I showed you earlier. And we'll select an unstable mode and just apply it as part of the initial conditions. And then we're just adding a random signal just to add more realism. So we essentially construct that environment where we have an unstable wave traveling in a channel flow superimposed to a mean flow. And then, so essentially, we then apply it. So we then monitor what happens. So unlike what I've showed you before, where we had where offline we had our phononic structure and we excited it by a force and see what happens to it. Now the phononic structure will be applied to the flow field, and the excitation will come from the flow itself. So this is the series of steps. We need to first obtain our unstable mode, then secondly, apply it and solve the full-fledged nonlinear 3D Navier-Stokes equations coupled with the P-sub, the phononic subsurface, and then as post-processing, track the energetics of the instability to see what happens to it under different scenarios. So quite briefly, here's the first step. We basically, as I mentioned, as a side step, before we start the analysis, we linearize the Navier-Stokes equation for this particular configuration for our channel, and essentially the way it's done is you assume a plane wave in the flow, similar to what we do in elastic waves, and that gives us a characteristic equation that we can solve for its eigenvalues for a given Reynolds number, and we can choose an unstable mode for a given frequency. So this is what we do. So now we have our unstable mode to apply, and we can identify where it is in this picture there that I showed you before. Then once we have that, we apply it to the model so that we can run a simulation. So the actual Navier-Stokes are solved in the main flow field region, and then in the solid itself we use finite elements. So it's a staggered solver where both are solved at the same time at every time step, and essentially apply appropriate boundary conditions between the flow and the solid. So we apply what's known as the transpiration boundary conditions. So this is small vibration interaction between the flow and the solid. So the surface essentially remains flat, and infinitesimal vibrations are being transmitted into the flow. So every time step, we evaluate the pressure field on the wall, turn that into a force, applies the solid, generates the elastic wave, and then the finite element code will give us back a velocity that gets applied back to the flow, and then we move on to the next time step and so on. So we run the simulation. We need to run it for quite some time in order to achieve steady state conditions, and then we track the instability. So we track the instability simply by picking up the perturbation part of the flow field. So these are the unstable modes, and integrating them over the volume and over time to get a measure of kinetic energy. In fact, we basically calculate the kinetic energy of our instability component of the flow. And if this kinetic energy drops, then that represents, or that indicates, stabilization. Otherwise, if it increases, that'll be destabilization. All right, so now let's see the results now. So what I'm showing you here on the left is the structural analysis without a flow. So this is the performance metric that I showed you before. The gray portion tells you where the band gap is, and the green portion, if you remember earlier, I said anytime you're negative, then that's stabilization, so green stands for that, and then the red portion is destabilization. Then on the right, I'm showing the kinetic energy of the instability using the equation I showed you before, and plotting that as a function of streamwise position. So you can see, so this is, we have the phononic crystal applied there, the P sub, and you can see the instability energy is growing downstream, and it's growing because obviously it's an unstable mode that is growing. That's by definition. And those two vertical lines just tell us where we will eventually put the P sub. So let's start with one example. So this example is an instability at a frequency given there by this dashed green line on the left at a certain frequency. And then you can see what happens to the kinetic energy. It basically drops exactly where the P sub is, and then practically recovers downstream to the P sub. So this is quite remarkable because it shows you that the energy of the instability has been manipulated exactly as we wish, exactly at the location we want, and it's done totally passively. Now we try another case. So this case has a slightly different frequency where it intersects at a slightly higher absolute value of the performance metric. It's still negative, so we get a stronger reduction. So that tells us that the higher the performance metric, amplitude-wise, the stronger the effect that we get. Well, that's expected because that corresponds to a higher resonant response, so a higher interaction between the solid and the fluid, so you get a stronger effect. Downstream, you see that the recovery is poorer, and in fact, we observed that there is a correlation between the value of the performance metric and not only the degree of the drop in the kinetic energy, but also the quality of the recovery. So there's a trade-off there in some sense. Now, on the other hand, if we try a destabilizing scenario, so we take this frequency there on the left, we see what we would expect. We see that the energy, instead of dropping, it increases. So we demonstrate successfully that we can destabilize that wave should we design the P sub such that that frequency lies at the positive value of the performance metric. And then if we try another value that is at a higher amplitude of the performance metric, then we get even stronger destabilization. So you can see a really perfect correlation that is determined a priori on the influence of the P sub on the instability in the flow field. So this I think one can then just really open up and imagine all sort of scenarios. So we can create a library of P subs, for example. Different colors represent different designs that intersect with the performance metric at different points, and think of this like a Lego set, and then we can get different levels of stabilization, destabilization in the flow as we want. So here's a video to help you visualize what happens. So what I'm showing there is only the U component of the instability field. So I'm not showing the whole flow. This is just the instability portion and specifically the longitudinal component, the U component. The left picture, both videos are the same, but the left one, the camera is fixed, and the one on the right, the camera is traveling with the instability. So the color code represents the intensity of the instability. So red means a lot of kinetic energy, blue means yellow means low. So I'll start running it, and somewhere in the middle, the P sub will be applied. So you'll be able to see what will happen. So look at the third slot. This is where the P sub will apply, and it's quite subtle. You will see that the color will turn more yellowish exactly where we apply the P sub. So you can see that this just beautiful wave interference, wave synchronization phenomena taking place all passively, the resonances and the anti-resonances, in this case, an anti-resonance effect in the flow due to designing correspondingly due to designing a P sub that acts at a negative phase. So negative phase gives us destructive interferences. So that's a snapshot you can clearly see between the control case at the back and the front case, you can clearly see that the instability has dropped exactly where we applied the P-sub. This is another simulation that shows the energetics in both fields, the instability field and the elastic field at the same time. So I would like you to observe it carefully. And you can see in the stabilization case, the amount of energy in the P-sub is less than the destabilization case. And again, that's analogous to what I've shown you before when I showed you the textbook notes on vibrations. If you're exciting a structure at an anti-resonance negative phase, you get less energy into the structure, and then vice versa if you're exciting it at resonance. And we're seeing this exactly unfolding, but now the excitation is coming from the flow itself. And subsequently, these phased effects are transmitting into the flow and causing stabilization versus destabilization, respectively. So that's sort of like what I was talking about earlier in my title, where we see perfectly synchronized response between the flow field and the solid field. And you can see it here more clearly. So this is, again, the same picture, but shown in a different way. So the color scheme shows the instability field altogether, not just the U component. And then the P-sub, we're showing the total, so that's the perturbation kinetic energy in the flow, and then the elastodynamic energy in the solid, both kinetic and potential energy in the solid. And so you can see the distribution there for the case of stabilization. You can see that in the contour plot in the flow, exactly where we apply the P-sub, the energy gets subdued because you get less energy in the instability field due to these destructive interferences. Now, to put this in perspective, if we look at the rigid wall case, you don't see that effect. And in fact, if we design a P-sub to act in a neutral sense, neither passive and neither negative phase or positive phase, we will effectively recover what we'll get from a rigid wall. And then on the other extreme, if we design it to destabilize, we'll get the opposing effect. And you can see there in the contour field in the flow, you get an increase in the instability, and then correspondingly in the solid, you get higher energetics in the solid. So this was a phononic crystal. Obviously, a phononic crystal is too large, so we later on analyze this problem using an elastic metamaterial, which is much smaller, 5 centimeters instead of 2 meters. And here's the results based on elastic metamaterial, even stronger. You can see the stabilization so clear there. And then these are the two reference cases. And then here's the destabilizing case. You see a clear concentration of increase in the yellow portion of that contour, suggesting a localized increase in the kinetic energy of the instability. So we can also calculate the skin friction coefficient on the surface. So you can see a correlation between the drop or increase in the kinetic energy of the instability versus the skin friction. So that's also very desirable because you can then directly control the level of drag, skin friction drag, by this mechanism locally. Not to mention also by delaying transition, you'll get the even bigger effect of avoiding turbulence. So going back to the original picture, remember I showed you this idea of energy transfer between the mean flow component and the instability, and then our interest, if we want to stabilize, is to reverse that trend. So let us now look at how this actually unfolds in the flow itself. So let's look even more precisely into the energetics of the flow field. So that's the instability component. I've showed that to you before. It's growing. Now, we can also plot the mean flow component. And so the mean flow component drops as the instability component increases, obviously, because that actually is consistent with what I was showing you before, that the energy is going from the mean flow to the instability. Now, it increases a little later because even without applying a P-sub, the picture here the P-sub is not applied yet, but it increases later downstream because the mean flow starts getting affected itself. So in a way, that's sort of like, you can view this as the very early stages of birth of turbulence. It's beginning to increase. Now, once we apply the P-sub, in the most beautiful way, we see exactly what we were talking about earlier. We see the energy trends get reversed. So essentially the instability energy gets down, and correspondingly the mean flow increases. And then similarly, if we destabilize, we get that interplay between the energy in the mean flow and in the instability field. So this view of a growing instability and causing transition to turbulence can be reversed. Now, we can also look at the mean flow component by subtracting out the base flow, and these orange lines that I'm showing you there on the top left, you can actually see them in the simulation itself in the rigid wall case, the reference case. And then you can see when you apply the P sub at the top to stabilize, you see that you're opposing that trend. And in contrast, at the bottom, when you apply a P sub to destabilize, you see that you're enhancing that trend. So we can then look also at the production rate. So this is going into some detail, further detail into the flow energetics. So we can plot the production rate as a function of the y position. We can see that obviously exactly at the wall, because there is no stick, because there's no slip condition, there's no production energy. But as we go further from the wall, the rate of production of the energy in the unstable mode increases. This is without a P sub. So that's the profile of that production process. Once we apply the P sub, we reverse the production process, consistent with what I showed you before. So rather than positive production of the energy in the instability field, we get a negative production, and if we were to, and that's at the beginning of the P sub, at the leading edge. At the far end of the P sub, that trend reverses again because then, as I showed you, the energy recovers. And then we can get the absolute opposite once we look at the case for destabilization. Now, one of the really important aspects of this approach, not only that it's passive, it's also responsive. Quite often in the fluids literature, people do experiments where they actively control that intervention, and it really gets so complicated because they have to either phase lock the instability or track it, so that when they apply the active control, they apply it exactly at the right time to destructively interfere with the flow profile, with the wave profile. Where here in P-subs, we absolutely don't need to do anything like that. It's all responsive, it's adaptable. So whenever the excitation comes, it just simply responds at a negative phase, regardless where we apply the P-sub, as demonstrated in this picture. Now, more recently, we started applying several P-subs in a row to extend the spatial domain. So you can see here very interesting results. The first one on the top is without a P-sub. The one after it is a single P-sub, which is what I've been showing you before. And then going down further, we start considering sequentially cases where we increase the number of P-subs. So the third one from the top is 2 P-subs adjacently applied, installed, then 3 P-subs, then 4, then 5. And you can see the green line represents the kinetic energy of the instability when we're intervening to stabilize the flow, and then vice versa. If we're intervening to destabilize the flow, that'll be the red part. And you can see that it's very consistently going underneath or above as we desire. So it shows us that if we want to, for example, cover the full span of the airfoil in a wing, we can simply apply that P-sub across all the way, and everywhere it's applied will reduce or increase whatever function we want, mostly reduce if we want to reduce drag across the whole spatial domain. And that would translate to delay in transition to turbulence, because you're reducing the amount of kinetic energy in the instability. You're basically slowing down the growth of that wave. Similarly, we can, as I showed you before, we plotted the skin friction drag. So the skin friction drag can be plotted also for multiple P-subs, and you can see a very clear, consistent trend as we add more P-subs on whether we are stabilizing or destabilizing. So finally, we find it useful to introduce a figure of merit to this idea, whereby essentially, if you look at the figure on the left, where we characterize the P-sub offline before we do any simulation, essentially, if we're interested in stabilizing the flow, what we would really need is to design the phononic structure, whether it's a phononic crystal or a metamaterial or any other type of phononic structure, such that the green portion in the plot here gets larger. So we want it deeper and wider. Deeper gives us stronger intervention. Wider gives us broader frequency range. And then if we wish to, so that can be, we can essentially define the area under the curve, APG, and our figure of merit will be that area. And our goal moving forward is to improve designs of P-subs to increase this area. And then in analogy, if we are interested in destabilizing, then the red region will be our area. So I like to sort of make an analogy with solar cells. When solar cells were introduced back in the mid-70s, the efficiencies were very low, but the concept was very promising. So different research groups from different parts of the world over several decades continuously explored different designs and ideas and so on, and the efficiency increased. So I hope that we can perhaps draw an analogy there and use those two metrics, and with innovation from specifically from the phononics community in terms of band gap engineering and control of resonances using unit cell design and truncation characteristics, which would draw ideas from topological phononics and so on. So our community is really very equipped, I believe, to tackle this problem and increase the performance metric with time. Eventually, we'll reach a point where the performance metric is big enough and wide enough to make it applicable for industrial proliferation. And given, so this is really our goal. And given that in both aircrafts and marine vehicles and long-range pipelines and wind turbines, the trend has been clearly going towards composite materials. This in fact makes the P-sub concept very amenable, because a composite is essentially a fiber reinforced plastic. So the plastic part, the polymer part, is the part that interfaces with the flow, and it's relatively compliant. It's still stiff. It's not like rubber, for example. It's still functionally stiff, but relatively compliant. That makes this concept very suitable for fabrication and integration into vehicle design and so on, using additive manufacturing and so on. So finally, just to leave some minutes for questions, there's a lot of people I want to acknowledge in addition to the funding agencies. So my students, past and present, their names are there. Specifically, I want to mention Armin Kianfar, one of my current students, who's produced a lot of the new results I showed today. Also want to mention collaborators. There's some collaborators from different, from CU and also from the AFRL, who are keen on examining the experimental side of this work. They're looking into building some experiments. And then lastly, I want to also specifically mention my former students, Osama and Alec, and then my dear friend, my late friend, Sadat Birinjan, who started this with me. He's a fluid mechanician. And this is a special moment picture where in early 2014, after really almost, I would say, probably 2 years of exploring this problem, we finally were able to get the recipe that I just shared with you today, where essentially everything has come together. So with that, I'd like to summarize. So just in brief summary, what I've showed you today was the synchronization of wave motion, phase synchronization of wave motion between a flowing flow and an attached solid, the phononic subsurface. And the outcome is essentially what we can view as a new approach, new paradigm for passive intervention and command of complex fluid dynamics phenomena using subsurface phonons. So we have a few references here if you're interested, as well as a book chapter. So I'm happy to answer any questions. Oh, this is absolutely true. So this is, I think this question is more on the applied side, which will be very relevant down the road. So the instability is a function of the Reynolds number. So the speed is built in the Reynolds number. So for any given speed we're interested in, suppose we're if the performance metric value is strong in the negative, then the drop in the kinetic energy is strong, but the recovery is weak. So there's a trade-off there. So if you're more interested in the recovery, then you would have to make sure that the drop is not that strong, so that you get good recovery, and vice versa. So there are subtle relationships there, but I should also mention that there is an opportunity to design how the P sub is applied to the surface in different ways. So what we have right now is a non-contiguous installation. So the P sub is very narrow, I should say, in these cases on the order of 1/4 of the wavelength of the instability wave in the flow. So in the cases I've showed you so far, the P sub acts like an elevator. It goes up and down, uniformly. Alternatively, we can have a contiguous connection, and then you get an elastic profile, more like a parabolic profile on the surface, and that will give us a better recovery. So to answer your question, we have some knobs to control the recovery. But the idea is that if we want to apply this concept to have very precise local control, then you do want this recovery.